Today we talk about chapter 15, liquids and solids. Probably what's going to happen today is we don't do all of chapter 15 in 101. We do the first part up to the crystalline solids, the unit cells. That's what Helene is going to talk to you guys about on Monday, but that's not going to be on the test. So anything that I don't finish today that I need to cover in chapter 15, I'll finish up in discussion on Friday this week and then Monday next week. And that'll be it. And then you'll be finished with the lecture. Wednesday, a week from today, is your next midterm.
When's the final class?
The week after that.
2 weeks after that?
2 weeks from today.
Oh,
2 weeks from today. No, 2 weeks after that. Good try. All right. So first, I'd like to develop at least somewhat of a picture for you guys of what we mean when we talk about solids and liquids. You probably have a good one already, but you guys already have a picture of a gas. That's the kinetic molecular theory. Hopefully that picture is pretty solid. A liquid, okay, is different from a gas in that the particles of the liquid, particles that make up the liquid, are touching each other. Remember, part of the kinetic molecular theory of gases says that the particles themselves are, on average, really far from each other compared to their size. But in the liquid, they're not. They're touching. But they're still moving. Okay? Just like the particles in a gas are zooming all around inside, the particles that make up a liquid are moving around constantly, all the time. But they're bumping into each other, they're touching each other all the time. There's not a lot of space between them compared to their size. But just like in a gas, just as the temperature is proportional to the average kinetic energy of the gas particles, we can say pretty much the same thing for a liquid. That the temperature of a liquid is proportional to the average kinetic energy of those liquid molecules. The hotter the liquid, the greater the average kinetic energy of the molecules in the liquid, particles that make up the liquid. In a solid, okay, the particles are touching each other also, just as they are in a liquid, except that instead of moving around, they're fixed relative to each other. Okay? They're not exactly static in a solid. In a solid, you say, imagine just, say solid krypton or argon, something that's just monatomic, so you don't have to worry about anything else. You have, say krypton. You have an atom of krypton here and an atom of krypton here. And then come back a couple minutes later, the same atom will probably be here, this same atom will probably be here. But at any temperature above absolute zero, 0 Kelvin, there's going to be some motion, right? Some vibrational motion with the monatomic gas, or solid rather. If it's a molecule, say it's ice, right? So now the particles that make up that solid aren't just single atoms, but they're molecules, and they have more degrees of freedom. There's more ways they can move. So you know what a molecule of water looks like: an oxygen and 2 hydrogen atoms, right? So in a solid piece of ice, the molecules are fixed relative to each other. There's a molecule here and a molecule here. Come back later, they're probably going to be in the same place. But again, at any temperature above absolute zero, those molecules are going to be oscillating. And within that molecule, the bond between, say, the hydrogen and the oxygen is going to stretch a little bit and contract, like they're connected by springs. Get that picture? And then the 2 hydrogen atoms, they can bend up like this, right? Just like they're connected by springs. You can twist a little bit, right? There's several different kinds of motion, right? And that's where the kinetic energy in a solid goes. The hotter you heat it up, the more thermal energy you put into that solid, the greater those oscillations, right? those movements, right? When you melt a solid, okay, as you put energy in, those, starting with ice, solid water, as you put energy in, those oscillations start increasing in amplitude and their energy increases. Until you reach the point where they have enough energy, those molecules of water have enough energy to break free of each other, and they start moving around. That becomes a liquid. You keep heating that liquid up. Okay? As you put more thermal energy into that liquid, those molecules are going to be, bumping into each other, moving around faster and faster and faster. The average kinetic energy is going to increase until they have enough energy. Well, it's a gradual thing, and I'll get to the details. But basically, you reach a point where now they escape from the liquid phase and go into the gas phase, and it vaporizes, evaporates. There's more to it than that, and I'll talk about that. But that process that I just described, taking some ice at some temperature below its freezing point and adding energy until it becomes a gas, you can plot that process. There's a much better graph in your textbook on page 521. So if we start out at some temperature below the freezing point of water, say, I don't know, minus 10 degrees Celsius, as you add energy, temperature's going to go up. Until you reach the melting point, about 0 degrees Celsius. At that time, as you keep adding energy, the temperature stays constant. Just like if you guys did the lab today, just like it was supposed to happen when it was coming back down. Remember that? If you do it tomorrow or the next day, you'll see the same thing. Temperature stays the same. This is not the scale. Until all of that solid has been converted to liquid. In between here, so in this time from here to here, initially, this is all solid ice at 0 Celsius. As you add more energy, time goes by, some of it starts being converted to liquid. Until at this point, right here, say, all of that water is now liquid, but still at 0 Celsius. You guys following that? Once it's all liquid, now the energy goes into increasing the temperature. The temperature starts going up again. Until you reach the boiling point of water at 100 Celsius. At that point, right at this point right here, you have all the water is liquid at 100 degrees Celsius. As you keep adding energy into it, it starts going from liquid to a gas. But it all stays at 100 Celsius during that whole process. It goes like this. And finally, after it's all been converted to a gas, the temperature starts going up again. In this class, we stop there. We don't go past the gas. We don't do plasmas or anything like that. So if we break this up into regions, it's all solid here. Where the line is flat, it's a mixture. It's a solid plus the liquid, right? The S is solid, the L is liquid. Over here, it's rising again. It's all liquid. And then here, it's going from liquid to a gas. In between, it's a mixture. And out here, it's a gas. Tried to show the right slopes, or relatively the right slopes, but you see the slopes of these lines where it's not flat? This angle right here, say, this angle right here, this angle right here. that depends on the heat capacity, the specific heat capacity of that phase. The specific heat capacity of solid water is different than that of liquid water, which is different than gaseous water. The greater the heat capacity, the greater the specific heat capacity, what do you think? The smaller the angle or the bigger the angle?
Small. What?
Think about it, right? What I'm asking is, okay, what I'm telling you is that the specific heat capacity of a solid, of ice in this case, this right here, is different than the specific heat capacity of liquid water, which is different than the specific heat capacity of water vapor. So they're going to, okay, and I'm also telling you that the specific heat capacity is going to affect that angle, if it's drawn correctly. I just did it by eye, but in real life it will. And my question to you is, will a greater specific heat capacity mean a smaller angle or a bigger angle?
Smaller angle.
I say bigger.
So we differ in opinion out there, right? So, okay, remember, this is time, so time's constant on this axis, right? So what does a bigger angle mean? Is it taking longer to change the temperature? In other words, or is it taking less time?
Longer.
Taking longer. What is a greater specific heat capacity going to do? What is specific heat capacity?
Speed up the, or doesn't speed up.
1 degree Celsius.
It's yeah, I mean, okay, it kind of
Sort of
combines
finish
this,
the
right?
sentence.
Yeah. So the specific heat capacity of the substance is the amount of energy it takes to raise the temperature of 1 gram of that substance by 1 degree Celsius. The greater the specific heat capacity, the more energy it can absorb before temperature goes up, right? The longer it takes it to increase the temperature. Well, assume that temperature is going in at a constant rate, and that's what's implied here, then a bigger angle means it takes longer to add the same amount of energy. Do you guys see that? So, bigger angle means greater specific heat capacity. Does that make sense? Well, one of the things that we're going to do is we're going to calculate, for instance, the total amount of energy it takes to take a certain amount of solid at some temperature beneath its melting point and convert it into a gas some temperature above its boiling point. I'm going to label these so that I can do the math over there. First section, where the slope's increasing, we call it A. Then where it's flat, B, increasing C, flat B, increasing. To calculate the amount of energy required to go up a slope line, all it is, like say for A, Q is equal to MC delta T. That's right. You guys, you know this equation already, right? Where S stands for the solid. I guess that's probably bad notation because we use CS to stand for the S to stand for just the heat capacity. How do we do this? Let's make it easier. Always molar heat capacity, capital CP. Yeah. So we'll use this. So N is the number of moles. This is the molar heat capacity of the solid. This is the change in temperature of the solid. For the flat lines, the Q, the amount of thermal energy required to make that process occur, is just equal to the moles times the change in enthalpy for that process. We call the process of melting, we call fusion. And so this is delta H of fusion. And we can look these numbers up, okay? I'll tell you what they are for. You don't have to memorize any heats of fusion or anything like that. For line C, it's just going to be number of moles times the molar heat capacity of the liquid times the change in temperature of the liquid. Just like this, only it's for the liquid instead of the solid. For line D, number of moles times the enthalpy of vaporization or the heat of vaporization. That's just like the heat of fusion, the heat of vaporization or the change in enthalpy of vaporization, just the amount of energy required to vaporize 1 mole of the liquid. And E, oops.
Specific, yeah.
When I say heat of fusion or delta H of fusion, it's just for this process, just to make sure we're clear. Vaporization, same idea. And these depend upon the temperature. Think about water, right? You can water will vaporize at temperatures beneath its boiling point. If you leave a bowl of water sitting out on the table, eventually you come back, all the water's gone, right? Because it vaporized, right? And it takes a different amount of energy to vaporize, say, a mole of water at room temperature than it does to vaporize a mole of water at its boiling point. Which do you think is going to be greater? Delta H of vaporization at a lower temperature or delta H of vaporization at a higher temperature?
Lower temperature.
So does it take more energy to vaporize the same amount of water if it's cold or if it's hot? It takes more energy to vaporize it if it's cold, right? Because you have to heat it up and and then vaporize it. Another way of thinking about it is the picture, right? Remember, the temperature is proportional to the average kinetic energy. So if it's colder, then the average kinetic energy is less. What has to happen for it to vaporize? The molecules have to leave the liquid phase and go into the gas phase. Right? They have to pull away from those other molecules. You guys know water is a polar molecule, right? Yes, you do. And so, if you imagine a container with liquid in it, at the surface of the liquid, you have all these polar molecules, right? Water. And beneath it, there's more of these molecules. There's tons of them, right? Well, at least 10 to the 23rd or so. You see this picture? So for this molecule to escape into the gas phase, it has to pull away from the other molecules around it. It needs some amount of energy, right? At a colder temperature, fewer molecules will have enough energy to do that. Right? At a higher temperature, as you increase the temperature of that liquid, more and more molecules are going to have enough energy to escape. It's going to be easier for them to escape. You're not going to have to put as much energy in. So, the heat of vaporization at a colder temperature is going to be greater than the heat of vaporization at a higher temperature. That makes sense to you guys? You guys know about vapor pressure already, right? Vapor pressure of water. Dalton's law of partial pressure is collected over water. Is that familiar? Remember you looked up in the lab the vapor pressure of water depending upon the temperature. And you know that the vapor pressure of water is the partial pressure of water above that liquid at temperature. Right? The more molecules there are, the greater the vapor pressure. You know that too? Maybe? Let me draw the picture again. So a molecule escapes, let's put a lid on it. And it goes into the gas phase, right? So imagine starting with this container and not having any water molecules up here at all. Then you put a lid on it, and you let the water molecules start to escape. Okay? They're going to, as they first start escaping, there's not going to be very many water molecules up in the gas phase. When they do escape in the gas phase, they're going to zoom around up there doing the things that gases do. Our kinetic molecular theory of gases, that picture, right? Maybe once in a while, one of them would happen to hit the surface and then get grabbed by the liquid and go back down to the liquid phase. But most of the time, there are going to be more water molecules escaping from the surface than there are recondensing. Make sense? Until, okay, so what, as that happens, most of the water molecules that escape stay in the gas phase. A few of them may be recondensed, but all the time, more water molecules are escaping from the surface. So you're putting more and more water molecules up in the gas phase. The more water molecules there are up there in the gas phase, the more there are going to be condensing at any given time. Right? Just greater chance, right? You guys have that picture? You see that then it makes sense that eventually you're going to reach the point where the number that are escaping, evaporating, is equal to the number that are condensing. Or the rate of evaporation is equal to the rate of condensation. Right? You're at equilibrium there. When that happens, when the rate of evaporation is equal to the rate of condensation, then the vapor pressure of water, or whatever the liquid is, that's what we call the equilibrium vapor pressure, and that's what you look up in the table at that temperature. So as you increase the temperature of the liquid, more and more water molecules are going to have enough energy to escape, because as you increase the temperature, the average kinetic energy increases. The more that have enough energy to escape at any given time, more are going to be escaping. You're going to be putting more up into the gas phase, so you're going to have to, there's going to be more up here when you reach this equilibrium. More molecules means greater pressure. So as you increase the temperature, the vapor pressure of the liquid above the liquid increases. All right, okay so far? Next slide. So these are both dependent upon temperature. That's what that whole thing is about. Going back to this. We'll do an example. get that written down, we'll work it out. As you're writing that down, you can see that the heat capacity, the molar heat capacity of liquid water is a lot greater than that of ice and steam. Ice is a little bit greater than that of steam. So this should have been the steepest line, and this should have been the smallest angle, and this should have been the biggest angle, and this should have been not quite as steep as that one. Right, because we said the greater the heat capacity, the greater the angle in this graph. So you guys have that all copied down?
Yeah.
So what we're going to do is take ice from minus 17.23 degrees Celsius up to 114.7. Figure out how much energy, first of all, it takes to do that. And to do that, we're going to figure out each of these sections one at a time, just like it shows over here, and then just add them up. Make sense?
Yeah.
And then the second part says, how long will it take to do this with an 1100 watt microwave, typical microwave, right? Do you guys know the units of what a watt is? It's a joule per second, right? So think about that as we're working this out. But the second part's, it's one step, it's easy. Right? So I'm going to erase this so that we can work over here. So we're going to calculate QA, B, C, D, and E, then add them up. For all of these, though, the N stands for the number of moles. I gave you the number of grams, so we're going to need to know the number of moles. That's easy. That's just the molar mass of water. And then for QA, it's the moles times the molar heat capacity of the solid times the change in temperature. So that's the moles, and you guys see that the same N carries all the way through. It's the same amount of water, so that number, that's going to be N for all of our calculations here. The molar heat capacity of the ice is 37.7. What's the change in temperature?
17.23.
Is it negative or positive? Positive. Because it's final minus initial, right? Final is 0, initial is negative 17.23, so minus is positive. What about that it's in Celsius and this has Kelvin?
Doesn't matter. Same
It
scale.
does the same, right, the difference is the same, right? Are you guys all comfortable with that? So I'm just write Kelvin so the units work out.
That,
We'll go back and get the numbers.
right?
Yeah.
And also.
QV, moles again. The heat of fusion is 6,010, right? No, I have the wrong units over here. Temperature's not changing, right? So there can't be any Kelvin here. These have to be per mole. And the same thing here. You guys go back in your notes and change that. You see? Same. Molar heat capacity of the liquid, 75.3. What's the change in temperature? What's the delta T of the liquid? 100, right? Final is 100, initial 0. Just like that. We'll make it 100.0. Well, actually, it doesn't matter. Just leave it. Section D on the curve, that's where it's flat. It's going from liquid to a gas. Vaporization is 40.65. And finally, E is where it's all vapor, and then the temperature starts going up again. The molar heat capacity of the steam is 33.6. What's the delta T for the steam? Good, 114.7 minus 100. This is 14.7. All right, so all we have to do is get these numbers, add them up. That's the answer to the first part, right? You guys get that number? Yeah.
Yep.
agree on those numbers? See, tens place, hundreds place, hundreds place, hundreds place, tens place, so we keep the hundreds place. About 392,900 joules or so. Did you get that number? Good. All right. How about the second part of the question? One watt is 1 joule per second. So it's an 1100 watt oven. And we need this many joules. How to figure out how long it's going to take? Exactly, right? The joules divided by the joules per second. That's all, right? Easy. Four sig figs, get 4 sig figs. So about 357 seconds, or just under 6 minutes, right? It's about 6 minutes. Went home, did that experiment, right? If you could get ice, you probably get ice down to minus 17.3. Be hard to tell if the vapor was up to 114%, so you really couldn't do it. But suppose you could measure the temperature, right? Would that, do you think that'd be the answer? Is that how long it would really take?
Close to it.
What's that?
Close to it.
Close to it? Why close? Why not it exactly?
Because that's ideal, isn't it?
What?
That's ideal.
Yeah, well, pretty much, right? That's theoretical.
Yeah.
But you have, in real life, you have to take into account things like, okay, if it's an 1100 watt microwave, that's how many joules per second it's producing, but is it all being absorbed by whatever's in there, right? Yeah. Now, the newer microwaves, I think they can bounce the microwaves around and, you know, get pretty good absorption, but you're still not going to get, you know, 100% efficiency. So there's, you know, a couple other things that we can count. But that's how you do that type of problem. Look for that in the homework and maybe on the test. Something like that. I told you about the heat of vaporization, heat of fusion, heat of sublimation, delta H of sublimation. You guys know what sublimation is, right?
From solid to vapor?
Yeah, solid directly to a vapor. Because enthalpy is a state function, it's just equal to the heat of vaporization plus the heat of fusion, or the other way around, doesn't matter. Right, because to sublimate something, first you have to convert it, well, this isn't what really happens. If something sublimates, it goes directly from solid to a gas. But it doesn't matter what path you take to get there, the change in enthalpy should be the same because enthalpy is a state function. So if you imagine going directly from a solid to a gas, take the same amount of the substance, go from a solid to a liquid to a gas. It's a different path, but you start at the same place, you end at the same place, right? So the delta H should be the same. You guys buy that? Not really, Travis? You don't, yeah, I can tell you don't believe me, that's okay. Do you remember, I know you remember, but did you buy into the enthalpy being a state function thing? Okay, and you remember, okay, so state function, remember, I think an example that I used was going from, say, here up to the top of Half Dome, didn't matter which path I took. Same thing right here, okay? We're going from here to Half Dome, we're going from solid to gas. Same thing, we're starting in one place, we're ending the same place. Because it's a state function, it doesn't matter what path we take to get there. I can run around the world and run up the back of Half Dome, or I can get in a helicopter, right? The change in height, elevation should be is the same, right? Doesn't matter what path I took. Where I started, where I ended, that's it. Enthalpy is a state function, doesn't matter what path I take to get there, it just matters where I start, where I end, right? If I started a liquid, and I started a solid, ended a gas, I can either go directly there, sublimated, or I can go from a solid to a liquid to a gas. The change in enthalpy should be the same, because it's a state function. You buy that now? So what that means is, sometimes when, as a practical matter, when you're looking up numbers, right, you don't always find the heat of sublimation, depending upon where you're looking, but you can almost always find heat of vaporization, heat of fusion. So if you need the heat of sublimation, just add these two together, and it's equal to that. Say on an exam, right, I ask you to calculate the heat of sublimation of something, and I give you information to find out heat of vaporization and heat of fusion, just add them together. You're next. So that's some of the things that solids and liquids do. Now we talk about why they do what they do. And that pretty much depends upon what are called intermolecular, your book calls them van der Waals forces. Forces of attraction between the particles in the solid or the liquid. Right? They're close enough together now so that the interactions between them are important. Remember, in our kinetic molecular theory of gases, we neglected any interactions between the particles. That was part of the kinetic molecular theory. Because for the most part, on average, they're really, really far apart from each other compared to their size. But in a solid or a liquid, they're touching. So you can't neglect the interactions. That's what we're talking about here. Intermolecular forces or van der Waals forces. types are these. And the order that I've listed them is the strongest the strongest per interaction on top down to the weakest. Ionic forces we've already talked about those. That's basically Coulomb's law. That's what you see in ionic compounds. Positively charged cation, negatively charged anion, opposite charges attract. That's it, right? The next two are related to each other. They're all really related. So I'm going to talk about dipole-dipole forces first, and then explain how hydrogen bonding is pretty much a special case of dipole-dipole interactions. So in order to have dipole-dipole interactions, you need a permanent dipole in the molecule. And what that means is that it has to be a polar molecule. And you guys know how to predict that, right? Lewis structure, geometry, look at differences in electronegativity, all that good stuff. So we're still doing that in this chapter. Was that chapter 10? That sound right? 9 or 10? Maybe 9. Somewhere back there.
Probably like 10.
Whatever it was. But whatever it was, you still have to do it, right? So make sure you didn't just toss it out of your mind yet. Start with a real simple example. Now I need to find that chapter because I need to. So hydrogen's about 2.1, chlorine's about 3.0, right? Close enough? You guys don't believe me. All right. Chapter 9, I think it was. Was it? 8 maybe. Way back there, right?
I started on 2.3.
Thank you. Yes, exactly. So chlorine's 3.16, hydrogen's 2.1. And that puts it as a polar bond, right? A polar covalent bond. You guys remember all this stuff? Which means that there's a little negative charge on the chlorine and a little positive charge on top. So never mind. Thought I wasn't looking, huh? Positive end and negative end. We have a couple of these molecules that come together. they'll naturally align themselves so that the negative end of one is by the positive end of another.
Okay.
And there's an attractive force between the two. Right? Just like in ionic compounds, but to a smaller degree. The size, the magnitude of this interaction is smaller. And the reason is that this is not a full-blown negative charge or a full-blown positive charge. It's a partial negative charge. It's less. The magnitude of this negative charge is less than that of the charge on an electron, and this is less than the charge on that of a proton. But there's this attractive interaction. That's the source of dipole-dipole interactions. You have this anytime there's a polar molecule that come together. Hydrogen chloride, you're used to seeing that as hydrochloric acid. That's when it's dissolved in water, when it's an aqueous solution. But hydrogen chloride can exist by itself. When it does, it's a gas, right? And we can look at that gas and we see that they actually cluster together, right? They don't condense as a liquid at room temperature, but we see this interaction. Okay. Hydrogen bonding. What you need is a hydrogen that's directly attached to a fairly electronegative element that has lone pairs on it. And it ends up that criteria is only met by 3 elements in the periodic table: nitrogen, oxygen, and fluorine. For example, water, right? Lewis structure looks like this. You know that because there are 4 electron groups on the central atom, 2 of those are lone pairs, the molecular geometry is bent, the angle's a little bit less than 109.5, right? Oxygen's more electronegative than hydrogen. 293, Pamela? 223. Oxygen's 3.44, hydrogen's 2.1. So it's a polar bond, but the difference is now that it's a really pretty polar bond, but it's not ionic by any means. But one of the atoms here is hydrogen. Now, hydrogen only comes to the table with 1 electron to begin with. All the other elements have more than that. Hydrogen only has 1. In this bond, in this single bond between hydrogen and oxygen, there are 2 electrons. One of them came from hydrogen. It doesn't have any other electrons. So what that means is that in the water molecule, the hydrogen atom is really just a nucleus, a sphere of positive charge with nothing shielding it, no electrons outside of it, because the only electron it came with is in that bond. Okay? And when you have a sphere of positive charge like that, that has a very strong attraction for a negative electrical charge. Another water molecule comes up. This fairly electronegative oxygen, okay, gets close to this. Here, because oxygen is really pretty electronegative, it pulls the electrons in this bond away from the hydrogen with fairly good strength, right? So the electrons in this bond are shifted away from the hydrogen. There aren't very many electrons around this hydrogen. It's that sphere of positive charge. when a water molecule comes, another one comes close to it, the lone pairs on the oxygen are going to be pulled pretty strongly over towards that hydrogen. Not enough to make a true covalent bond, and that's where some confusion comes in, I guess. But it's not hydrogen bonding. A hydrogen bond isn't really a bond. It's an intermolecular force, right? But it's a pretty strong intermolecular force because a lot of this electron density gets pulled up by the hydrogen, and it's held there pretty strongly. The more electronegative this element, the more the electrons are going to be pulled away from the hydrogen, the more electron density there is going to be on the oxygen, and the stronger the strength of this attraction, right? Now, in water, okay, oxygen has 2 lone pairs, so that means that each oxygen can make 2 hydrogen bonds. Does that make sense? Do this over here. Now, if we look at nitrogen being in there, that would be ammonia. You have hydrogen directly attached to nitrogen, so there's hydrogen bonding. Based on what I just told you, do you think that the hydrogen bond in ammonia would be stronger or weaker than that in water? Good. Weaker. Why? Nitrogen's less electronegative than oxygen, for one, and also it only has 1 lone pair, so it can only make 1 hydrogen bond. That makes sense? So that's hydrogen bonding, and you need to know how it comes about, when it exists, right? Make sure, one mistake that people make at first is they forget that the hydrogen has to be directly attached to one of these elements. Just because there's an oxygen in there somewhere and there's a hydrogen in the molecule somewhere doesn't mean there's hydrogen bonding. That hydrogen has to be right on that oxygen. Whatever. It's stronger than dipole-dipole forces, right? But not quite as strong as ionic forces. The weakest of these intermolecular forces are, your book calls them London forces. And every molecule has these. If there's electrons, there's London forces. The way they come about is this. Well, let's describe, say, argon. You can make argon into a liquid. It's a noble gas, right? But if you cool it down enough and you exert enough pressure on it, you can liquefy argon. In order for it to be a liquid, there has to be some intermolecular forces. Argon's monatomic, so it's certainly not ionic. It's not hydrogen bonding. It's not, a polar molecule, so there's no dipole-dipole. Must be something, right? What happens is this. If you imagine the argon atom, the nucleus in here, and then all of the electrons just as this big cloud around it of electrons. Well, those electrons aren't static. They don't just sit there in their orbitals, but they're constantly shifting. The electron density is constantly shifting around. Clouds, like just moving around all the time. And just because of their more or less random motion, at any instant it's possible that there might be more electron density on one side and less on the other. And if that happens, there's going to be a little bit of a negative charge that builds up over here instantaneously, just temporary, right? But, this is a neutral atom, so that has to be balanced by a little positive charge, say, over there. And this might, and it might change, the next instant, it might shift around, it might be negative down here and positive up here or something like that. But at some instant, you know, there's gonna be some dipole moment. So as this argon atom comes next to another argon atom, even if the electrons aren't shifted, they're evenly spread about here, this little negative charge here is going to repel the electrons in this atom, push them away, creating a little positive charge there and a little negative charge wherever they get pushed away to. It's created an instantaneous or a temporary dipole, right? And that interacts just like that. And that's another attractive interaction, right? Opposite charges pulling these together. This is enough to be able to liquefy and even solidify this if they're slow enough, right? If you cool them down enough, force them together enough with high pressure. You guys buy that?
And it depends on what element it is, right? Or what atom it is. If
Well,
it's gonna be
they all have it, right?
Yeah, but how much longer they're gonna stay together connected?
How strong? Okay,
How
that's
strong,
a
so-
good point. So how strong is this? Are these London forces?
Yeah.
Well, there's a couple of factors. And in general, the more electrons there are, the more they can shift around and the stronger those intermolecular forces. A shorthand way we have of saying more electrons is saying increased molecular weight, right? Because as long as we're talking about neutral species, the more electrons there are, the more protons there are, right? The more protons there are, the greater the molecular mass, right? So what we say is, in general, the higher the molar mass, molecular weight, the greater the blended forces. But if the molecular weight is relatively the same between different molecules, we also see differences, right? It ends up that this molecule here, N-pentane, at room temperature and pressure, it's a liquid. This molecule here there's carbon in the middle, right? There's 4 carbons around it. This has no hydrogens. Each of these carbons has 3 hydrogens. Here's what we know about these two relative to each other. This is here. We know that in this molecule there's more London forces, there's less London forces here. They have the exact same molecular weight. They both have 5 carbons and 12 hydrogens, right? Both C5H12. The only difference is their geometry, their structure. It ends up that if you build this molecule, you have a straight chain, and if you were to imagine all the electrons being on the outside of it, pretty much looks like an oblong, pearlite spheroid. you know, a balloon, right? Like to make a balloon. Whereas this looks more like a sphere. There's more surface area here than there is here. There's more places for this to contact other molecules than there are here. So there are more opportunities for London forces here than here. And that's why. So now, molecular weight kind of trumps this, especially if there's a big difference. But as long as the molecules we're talking about are pretty similar in molecular weight, then the more surface area there is in that molecule, the more London forces there are. So, okay, with all that under our belts, knowing these relative strengths, and for London forces, these relative strengths. What we can do with them is we can predict boiling points, okay, heats of vaporization, and a few other properties. Anything that depends upon the strength of the intermolecular forces, the stronger the intermolecular force, the greater the energy required to do that. Let's say boiling point, right? How much energy does it take to boil a mole of some compound, right? Okay, so what do you have to do to boil it? You have to pull the molecules from the surface of the liquid into the gas phase. You have to pull away. The stronger they're held in the liquid phase, the more energy you have to put in. What holds them there in the liquid phase, what holds them to each other, are the intermolecular forces. So the greater the strength of the intermolecular forces, the greater the boiling point. That make sense? That stands for intermolecular forces. So it ends up with these two molecules right here. At room temperature and pressure, this is a liquid. This is a gas. This has a higher boiling point than this because it has more of these London forces. They both only have London forces, right? They're both non-polar molecules. There's no other molecular forces involved, right? Which do you think would have a higher boiling point? Xenon or argon? Xenon, right? They're both monatomic, but xenon is heavier. Higher molecular weight, stronger London forces, higher boiling point. In general, ionic compounds have really high boiling points, right? Because they have really strong intermolecular forces. Heats of vaporization, same idea. We talked about vaporizing the water, right? Heat of vaporization, how it depends upon the temperature. Well, looking at the other side, that was looking at how much energy we needed to add to pull those molecules away. But if we look at how much energy, how strongly those molecules are being held in the liquid, the stronger they're being held, the more energy we have to put in, right? And so what that means is the stronger the intermolecular forces, the higher the heat of vaporization. Now, keeping the temperature the same, what do you think increased strength of intermolecular forces means for vapor pressure? The partial pressure, right? The vapor pressure of water, partial pressure. Remember that?
Lower vapor pressure.
More higher or lower vapor pressure?
Less.
Less, lower, right? The stronger those intermolecular forces, the harder it is for this molecule to escape, the less of them are going to escape at a given temperature, and the lower the vapor pressure. We just do surface tension. We do viscosity. Yeah, viscosity and surface tension, and we'll talk about equilibrium vapor pressure a little bit more in discussion when we finish. We've got a couple minutes. Surface tension. Imagine that beaker of water against. At the surface, and in the middle. Imagine a molecule of water right in the middle of that beaker of water. That molecule of water is surrounded on all sides by other molecules of water. They're all touching it, right? And every place another molecule is touching it, there's the interaction between the positive and the negative parts of the molecules. So you bring in positive and negative charges close together. That lowers the energy of that molecule. So this molecule has pretty low energy because it's surrounded by other water molecules with their opposite charges pointing in towards it. You guys buy that? Positive here, same picture, negative here. Molecules at the surface, same thing's happening, except above them. Above them, there aren't any molecules to do that. And so a molecule on the surface has higher energy than it does in the middle. You guys find that one? And what that means is, because everything in nature tends towards the lowest energy state that it can be in, given the opportunity, that molecules don't like to be on the surface, right? It's higher energy for them to be there. So what this is going to do, this liquid is going to try to minimize its surface area, right? Minimum surface area for a given volume is a sphere, right? You guys know that? Yeah. So what this molecule, one of the things, surface tension, this is surface tension, I'll do it in a minute, is doing to this is trying to form a sphere. Why isn't it a sphere? Motion of the molecules aren't enough to overcome that, because why? Gravity. Gravity's pulling it down, right? So the molecule is trying to form itself into a sphere, but gravity's trying to flatten it out, right? So gravity kind of wins here. But you go up into outer space, right, where there's less gravity, almost none, like in the space shuttle, and then it's going to try to form a sphere, right? Like you've seen those pictures, right? The astronauts up there, the globules of, you haven't? Look it up on YouTube.
I thought you were going to say Google.
If I were to take my finger and try to poke it through the top of this water, right? Think at the molecular level, think what has to happen. I have to push these water molecules apart, right, for my finger to fit in there. And they don't want to go apart because they're attracted towards each other, right? I have to overcome that attraction. That attraction per surface area, the amount of energy per surface area, that's the surface tension. The greater the attraction between the molecules, the greater the intermolecular force, the greater the surface tension. I'm out of time, so what I'll do in discussion on Friday and then again on Monday for each section is I'll talk a little bit about viscosity and then I'll do sections 15-6, 15-7, 15-8. So like